All right, so we were doing this. Uh, we want to show that E is not compact, right? Where E is a subset of a metric space which is not closed. Uh, since it is not closed, there is a sequence in Xn. There is a sequence Xn in E whose limit point doesn't belong to E. And then I use that sequence and its limit point to form an open cover for E which won't have a finite subcover. So you see, if I take finitely many of such open sets, note that any uh, finite number, let's say O and 1, O and K uh, of open sets, subsets, uh, won't cover E. Why is that? Because what is the union of these open sets? This is just so what are these? These are just uh, x minus these balls. So their union will be just x minus intersection of these balls. So this is just, you see, this is x minus these balls and I from 1 to k, and this is just x minus the intersection of these balls. I from 1 up to k. What is the intersection of these balls? Well, the intersection will be just the the ball with smallest radius. So this is just x minus b x0 1 over n0, where n0 is the maximum of this, or 1 over n0 is the minimum of these. So this is just the maximum of n1 up to nk. But clearly, you see, uh, so this thing doesn't contain the ball with radius 1 over 1 over n0 about x0, because you just deleted that. But that ball certainly contains some elements. Clearly, since limit of xn is equal to x0, uh, uh, some there is some index after some index, all xn's will uh, lie in this ball, and thus E cannot be a subset of this gadget, because infinitely many elements of E will lie inside this ball. Hence, uh, the open cover which open cover this O ends for E has no finite subcover. Thus, E uh, uh, is not compact. But again, we assumed at the beginning that E was compact, right? E was compact. And the reason we arrived at this contradiction is the following assumption again. We assume in the contrary that E is not closed. Which is a contradiction. Thus, hence E must be closed subspace, subset. Okay, so this finishes the proof. A corollary of this is the following. Okay, maybe I start with this remark. Now, any questions so far? Okay, so let me start. Okay, let x um, xt be a subspace of x tilde d. Okay. Uh, okay, so x is a subset of this. Any open set, take any open set u in xt. Okay, then we know that any open set is the union of open balls contained in u, right? If you take an open set, then any point here is contained inside some ball, right? Therefore, I can write this. This is just b x I and some radius okay, let me write it this way. Then for any x in u, there is some radius. So I take x here, there is some radius rx, there is some rx positive, so that this ball with radius rx lies inside u. Hence, I have this u, which is the subset, which is the union of this one element sets, right? I can write u as the union of one point subsets of itself, but each these subsets, lies in this ball, of course. So x in u, but each such ball lies inside u. Therefore, I have this. So what we see is then u is the union of some open balls. Any open set is a union of balls. That's the statement. But now you have the following. These balls lie inside the metric space X, right? So let me distinguish that. So I have this. So these are in the metric space X, let's say. But what is the distance? What is the difference between the balls in X and X tilde? You see, this ball, if you choose any epsilon ball, what is this? This is the set of all x's in X such that the distance from X, this is the set of all y's such that this is less than epsilon. What is this ball? X tilde x epsilon. That is just the set of all elements in x tilde such that the distance between x to y is less than epsilon. So what you see is that if you the difference between these two is the following. If I take this ball and intersect with x, so I take y's that lies inside x, you get just this ball. Okay, so we see the following. Hence this open set in x is contained in this uh, gadget. So here I take balls in x, and here I take balls in x tilde, and they form, of course, another open set, which is open in x tilde with the following. The intersection of these, this open set with x is just u, because this is the union of these balls, and when you intersect these balls with x, you exactly get these balls. So any open set in x is the intersection of x with some open set in x tilde. So when you have a subspace, okay, open sets of that subspace are basically open sets of the bigger space intersected with the subset X. Okay. Conclusion. In other words, any open subset of the subspace X is the intersection of an open set, open subset of X tilde with the subspace X. Okay. All right. Why did I tell you this? Well, the reason is the following. So this is a corollary of this observation together with the above theorem. If a metric space XD is compact, then it must be complete. Okay. So a compact metric space has to be necessarily complete. Okay. Proof is very easy now. Now assume on the contrary that X is not complete. Okay. Well, a space may not be complete, but we know that any metric space has a completion. Okay. Now let X tilde be its unique completion. We know that completion is unique up to isometry. There is a unique completion. And X is not complete implies that X is not equal to X tilde. So X is a subset of X tilde, but X is not equal to X tilde. because if it were, then X would be complete. So let X0. Okay, all right. Well, okay. Yeah, maybe I should write this. It's completion. Okay, since X is not complete, and any closed subset of a complete metric space is complete, we see that X cannot be a closed subset of X tilde D tilde, right? Because if X were a closed subset of a complete metric space, then X would be complete too, right? But by assumption, X is not complete. Therefore, X is a subset of X tilde, but that subset cannot be closed. So, X is not a closed subset of a metric space. It's a uh, uh, subspace of a metric space, but it is not closed. Okay, and since it is not closed by the above fact, it cannot be a compact subset. Hence, X cannot be a compact subset. Cannot be a compact subset of X tilde. Uh, and that implies that X is not compact. Why is that? You see, uh, now this doesn't mean that X is not compact. X is not a compact subset, but what I claim is more than that. Forget X tilde. I am saying that X is not compact. So I claim now X is not a compact metric space, is not a compact metric space. How I can prove this? Well, okay, take any take any open cover or alpha of X, then by the above remark, each O alpha is what? X tilde intersection U alpha for some open subset U alpha of X tilde. Thus, this U alpha is an open cover for X because they just, cover each O alpha, and O alphas cover X. So if I take an open cover for X, then I find an open cover for X, but this time this open subsets belongs to X tilde. Conversely, Conversely, if U alpha uh, is an open collection, is a collection of open subsets covering open subsets in X tilde covering X, then uh, this open set is an open cover for X, where O alpha is just X intersection U alpha. So if I start with an open cover for open cover U alpha for X, then just taking intersection of these open sets with X, I get open sets in X, and they cover X. This means what? This means that any open cover of X actually comes from X tilde, and if you start with an open cover in X tilde by just taking intersections of each open set with X, you get an open cover in uh, in X. Now I know that X is not a compact subset of X tilde. Uh, Now, since X an is not a compact subset of X tilde, there is an open cover. There is an open cover U alpha in X tilde, so that so uh, so that this open sets cover U alphas, but uh, no finitely many U alpha will cover X. But then, hence, if I take intersections of these U alphas with X, hence, if, okay, finally, let O alpha to be X intersection U alpha, then these gadgets, these are all open in X. Moreover, uh, this is an open cover for X, which do not have a finite subcover. Okay, because if finitely many O alphas would cover X, then finitely many U alpha would cover X, but that's not possible. Therefore, this O alphas won't cover X. So there is an open cover for X, which do not have a finite subcover. Hence X is not a compact metric space. This shows actually more than what this result says. Compactness is an intrinsic property. It doesn't uh, depend on the space or bigger space that contains X. Okay, it doesn't matter where X is lying, whether inside a bigger space or not. Compactness is related only to X. Okay, not to the space it belongs to. Okay, so let me write as a remark: this observation tells us that being a compact subset is an intrinsic property of the subspace E, okay, of X. Uh, if it is so, E can be a subspace of many different spaces, and if it is compact as a subspace of one of them, then it is compact for uh, a subspace of any other metric space. Okay, that so being compact depends only on E, not the space, bigger space that contains E. Okay, so that's the content of this remark. Okay, any questions so far? Let me okay, finish today's lesson by the following proposition, which we will make use of a lot later. Every sequence, so we will start considering sequences in compact sets. Every sequence in a compact set E as a subsequence which converges to an element of E. That's a very important result. So if you start with a sequence in a compact set, then it has necessarily a subsequence which converges to some element of E. Okay, how can we prove this? Well, again, we will uh, do by the method of contradiction. Assume that uh, there is a sequence in uh, there's a sequence, say xn in E, which do not have, which doesn't have any convergent subsequence. So this is a sequence so that it has no convergent subsequence. It has no convergent subsequence means this sequence doesn't get concentrated around any point of E, right? It doesn't converge to any point means around any points there is some ball, so that that ball contains only finitely many terms, right? Uh, Hence, for any x in E, there is some positive number Rx so that the ball with center X and radius Rx contains only finitely many, contains at most finitely many Xi's, right? Why is that? Because you see, if let's say I have a point so that any ball around this point, contains infinitely many Xi's. Then by just shrinking this ball, first I take with radius 1, I find some x1, and then I suppose there are infinitely many such elements. I choose one, and then I choose another ball with smaller radius. I pick another term from this sequence, and then I make the radius even smaller and smaller. So I get what? I get a sequence of terms, let's say xn1, xn2, xn3, so that you know uh, xn1 and 2 and k, so that the distance between these terms and I and x is less than 1 over I. Okay, well, clearly this subsequence will converge to x, right? Since there are infinitely many elements in each ball, I can choose this ni's in an increasing manner. So first I start with n1, and then I choose n2 so that the distance between, so that n2 is larger than n1. I can do this because in any ball there are infinitely many xn's. So if n1 is, let's say, 1 million, since there are infinitely many xi's, there will be some xi with index larger than 1 million. So you can always choose this uh, indices in an increasing manner so that you get a subsequence, and by the choice of this subsequence, this distances are less than 1 over I. Therefore, limit of xn is just x, so that it is convergent. But by the assumption, we assume that this sequence doesn't have any convergent subsequence. This means that for each x, there is some ball, and that ball contains only finitely many xi's. Okay, so the set of this i's is finite, hence uh, this set I such that xi belongs to xrx is finite. Okay, but you see, uh, and this is true for all, of course, x, right? For each x, uh, there are only finitely many uh, uh, indices, so that so for each x, I find some radius so that that ball contains some xi's, but the number of indices so that xi lies in that ball is finite. However, I have this, you see, every term xi lies inside one of them. So, so the set of natural numbers, which is the union of all these sets, right, I from 1 to infinity, uh, each xi lies in one ball because I can just choose the center to be xi and uh, okay, let me do not this way, this way. All right. Now x is equal to what? X is equal to union of this 1 point sets, not x. I should do for e because I had yeah, I have this e. But now each x lies inside the ball with center Rx, and so that these open balls cover E, so that this collection is an open cover for E, but E is compact. Since E is compact, E must lie inside finitely many of these. E is inside, let's say, Bx1 Rx1, Brx, uh, okay, maybe I should say not x but y1, y1, yk, ryk for some points y1, yk in E, since it is compact. However, you know, each such ball contains only finitely many terms of the sequence. Therefore, in this union, there will be only finitely many terms of the sequence xn. But xn, the whole sequence, lies inside E and it has infinitely many terms. And that's a contradiction because E contains infinitely many xn's, but each of these balls contains only finitely many of them. That's a contradiction. So here is the uh, final line. Since xn lies in E, we have the following. The set of natural numbers is is what? This is the set of all indices such that xi belongs to E, because every term of the sequence belongs to E. Therefore, I have this. But you see, this thing can be written like this. Okay, so that is equal to I such that xi lies inside B y1 ry1 union yk ryk. But you see, what is this? I belongs to, so I is an integer, so that xi belongs to one of them. But that is just the union of these. So, okay, I can write it this way. Okay, I can just stop at this point. So this is an infinite set, and I am looking at I so that xi belongs to one of these. This is a contradiction. since n is infinite and each byi ryi contains only finitely many şöyle diyeyim and infinite and each subset I such that xi belongs to y, let's say j r y j is finite. I use this different index because I don't want them to confuse, right? Each these sets are finite, right? Because these balls are chosen so that in each of them uh, there are only finitely many xi's, but finitely many of them contains infinitely many xi's. That's not a uh, that's a contradiction, and this finishes the proof. Okay, uh, we arrived at this contradiction because we assume that there's a sequence in E which doesn't have a convergent subsequence. Okay, uh, and we arrived at this contradiction. Therefore, every sequence in E has a convergent subsequence. Okay, yeah, I think I may stop at this point. All right, so next time we will, let's see. Okay, yeah. We will prove a big theorem, namely converse of this. Here we show that in a compact metric space, every sequence has a convergent subsequence, and we will see that actually that is equivalent to being compact. Namely, if every sequence has a convergent subsequence, then the metric space must be compact. Okay, so next time we will prove the converse of this. All right, so let me stop now.